In radiation therapy, charged particles such as electrons or protons, X-rays, and sometimes neutrons are used to treat cancer. This videotape is designed to help you understand how X-ray photons interact in tissue and some of the concepts of radiation physics that are important in determining the therapeutic outcome. These are the same interactions that allow a photon to be detected in an ionization chamber, a piece of X-ray film, a scintillation detector, or a thermoluminescent dosimeter. Photons are particles of electromagnetic radiation. Electromagnetic radiation comes in many forms, distinguished by the energy of the photon. The photon energy is related to the frequency or the wavelength of the radiation. All of these are electromagnetic radiation: radio waves, microwaves, infrared, visible and ultraviolet light, X-rays, and gamma rays. The only difference between X-rays and gamma rays is their source. X-rays are released by changes in the electrons in an atom, while gamma rays are emitted when the nucleus of the atom loses energy. There are 4 ways in which photons interact with matter that will be of concern to us. They are coherent scattering, the photoelectric effect, Compton scattering, and pair production. In coherent scattering, a photon scatters from an atom. Its direction of travel is changed, but not its energy. Here on the screen, I have a representation of a coherent scattering. We have a photon coming in from the left that is scattered from an atom that we cannot see, and the scattered photon has traveled off in the upward direction. The reason that coherent scattering will not be of interest to us is that it does not leave any energy in the tissue, since the energy of the photon is not changed. Coherent scattering is important, however, in diagnostic radiology, because the scattered photon can strike the X-ray film, contributing to the background fog, which reduces the quality of the image. The photoelectric effect is important for photons with energy below 50 kiloelectron volts striking water or soft tissue. In the photoelectric effect, a photon is absorbed by an atom and an electron is ejected. The atom is left in an excited state. Later, the excited atom loses its extra energy by emitting characteristic X-rays or Auger electrons. The amount of energy released by the atom is fairly small, and we will not worry about it in this videotape. Another process that can take place is Compton scattering. The photon interacts with an atomic electron, resulting in a lower energy photon moving in a different direction. The electron is ejected from the atom. Here is a schematic picture showing the results of a Compton scattering. We have the incident photon coming in. We have the scattering take place there. We have the scattered photon in blue coming down this way, and there is the track of the recoil electron. The scattered photon may leave the body, or it may also interact. The electron path is shown in red. The more energetic the electron, the longer its path or range. This is schematic. The electrons do not travel in straight lines, but it is shown that way here. If the incident photon energy is high enough, it is possible to have a process called pair production. The threshold energy for pair production is 1.22 million electron volts. In this example that we will see on the screen now, a photon of energy 10 million electron volts came in and underwent pair production. The photon interacted with the electric field surrounding the nucleus, and it completely disappeared. A negative electron and a positive electron were produced, and some of the energy of the photon was used to create the electron and the positron, 500,000 electron volts each, and the rest of the photon energy became kinetic energy of the electron and the positron. They lost that kinetic energy as they traveled along their path. Here is another pair production event where the original photon energy is higher. Now it is 20 million electron volts. The total energy of the electron and the positron is greater, and therefore they travel farther. That is, they have a greater range. When a photon enters matter, its interaction is random. How far the photon travels before interacting, and whether it interacts by the photoelectric effect, by Compton scattering, or by pair production, are determined by chance. The probability of traveling a given distance or interacting in a certain way is determined by the photon's energy. So if we do an experiment in which 1 million photons of a given energy interact, we know roughly how many will undergo each kind of interaction. But if we follow an individual photon, we cannot predict exactly what will happen. In this videotape, we are going to watch simulations of photon interactions. These will be done with this computer program called MacDose. I am now going to start MacDose running, and we will see the simulation of 25 photons. We are assuming that we have a parallel beam of photons coming in from the left. That is the same as saying that there is a photon point source very far away. MacDose also assumes that all of the photons have the same energy. In a real X-ray beam, there is, of course, a distribution of photon energies. MacDose generates a number at random to determine how each photon is going to interact in this water phantom. Here we have had 25 photons come in. Some of them have undergone Compton scattering. You can see the blue scattered photon. I don't see any photoelectric effects in this particular screen. If we repeat the simulation with another 25 photons, the details will be different, but the average behavior will be the same. Now what I'm going to do is to try to point out to you some features of particular interactions. And in order to do that, I'm going to have to fiddle with MacDose and change the parameters. In order to show you what I want next, I want to work with a 1 MeV photon. So I will say I will set my parameters. I will change from an energy of 100,000 electron volts to 10 to the 6th electron volts. I will set the beginning of my chain of random numbers to be 2. I'm going to set it up so that I will only display 1 photon on the screen at a time. And now what I will do is to run a single photon of this energy 1 MeV. Here we have the effect that I wanted. An incident photon came in. It got all of the through my phantom before it interacted. Then it underwent a Compton scattering. There is the recoil electron, and there is the scattered photon. The scattered photon disappeared out the bottom of my sample. What I have done is to imagine that that photon came back in through the top of my sample, and it came that far before it randomly interacted. While, of course, a given photon does not do that, nor is there always a photon coming in from the top that will exactly compensate for one leaving through the bottom, on the average, when a photon leaves through the bottom surface, some other scattered photon will enter through the top surface. What I want to do now is a simulation with 250 kilovolt photons. I have changed the energy to be 250 kilovolts, and I'm going to allow 25 photons to interact on the screen. When I do that, and I look at the results, I see that there were 4 photons which went all the way through my sample. We say that these 4 photons were unattenuated. In this case, 4 out of the 25, or 16%, were unattenuated. I can now send another 25 photons through the sample. And in this case, I see that 1, 2, 3, 4, 5 of them passed all the way through. In this case, the fraction which were unattenuated is 20%. I repeated this simulation for a total of 100 photons. After 100 photons had struck the phantom, the fraction unattenuated was 19%. Off camera, I then did 40 simulations. In each simulation, 100 photons struck the phantom. I recorded the fraction of the unattenuated photons that passed through the sample in each simulation, and on the screen you see a histogram which shows the number of times a given fraction was unattenuated. There was one occasion where 18% of the photons were unattenuated. There were 2 occasions when 19% were unattenuated, 2 occasions when 20% were unattenuated, and so on. And there were 3 occasions where 35% of the photons were unattenuated. The overall average was 28%. I then did the experiment longer. Instead of doing it for 40 simulations, I did it for 90 simulations. There is a mistake over here on the label. This is actually for 90. And we have a somewhat different histogram.